when we have bigger exponents, like a cube or a fourth or a fifth or a sixth, if I take this and I say, okay, my f of x is x cubed plus 2x squared minus 5x minus 6, I've already factored this for you, but our overall goal is going to be able to factor it. But in order to be able to factor it, we're going to have to know at least one component, one zero that actually exists. And we can do that by testing whether when we plug it in, it gives us a zero, right? Because basically whatever we plug in is going to give us what the remainder is, but we'll see that in a second. But if I plug in f of -3 into here, right? First of all, what should I get? And what do I get? Maybe just do that on your calculator. Just convince yourself that that's going to work out. Did you get 0? It should be 0, right? That's what it should be, as long as this is all done correctly. Based on the fact that if this is true here, then if I put it in here, then this would give me 0, and 0 times anything should be 0. So this should be 0, which would make x plus 3 a factor, right? But let's just double check. We'd have what, -27, and then plus 2 times 9, which is 18, and then plus 15, and minus 6 is 0. So it does equal 0. And we can actually get these things quite quickly. If you have a TI-83, you can use the table function in there to like guess numbers, and you're eventually going to have to do that, because what you'll be given, like where we're going with this is you're going to be given some random polynomial, and you're going to be asked to factor that polynomial, and that's a higher degree polynomial. So what that means is we need to identify factors. So we'll learn how to choose these factors in a bit, but assuming you know that x plus 3 is a factor, then that means that I should be able to take f, and I should be able to take f of x, I should be able to divide it by x plus 3, and it should divide evenly with no remainder, and it should produce the rest of it, x minus 2, x plus 1, right? Like if I take my x plus 3, x minus 2, x plus 1, now I'm like, you won't know this, but assuming we know this right now, if I divide by x plus 3, I should just get that back again, right? But the problem is it's not going to be factored for you. So we need to learn how to divide the polynomial, get, you would end up with this, because I just multiplied it out. And then you could factor it to that, and then you would get to the factored form. So that's our game plan strategy. So in order to do that, we need to learn how to long divide polynomials. And this is something that you would have done in previous courses, but maybe we need a bit of a reminder. There is a video online that'll show you this in detail, but essentially if we want to get to get from here to here, we're going to need to take this and divide it by one of those things once we know what it is. And then hopefully if we divide once, the cubic will reduce to a quadratic, and we already know how to factor quadratics. And our goal is to be able to identify all 3 of these zeros. And then eventually between those zeros, we can find maximums, minimums, etc. That's what this whole unit is about. Okay, that's our general game plan. There's 2 theorems here. They're really wordy, but so this is 3.1 in the textbook, or essentially it's like remainder theorem and factor theorem. On ALEX, it is questions after question 16, like 16 to 20 on Alex. And all this tells you here, if you just read it, well, we just did this. So if this polynomial has this as a factor, it is congruent of a statement too, because if and only if, to the fact that if you plug that number in, you'll get a 0. That's essentially what I just told you in the previous slide, right? Assuming that, so x plus 3 is a factor, means that if I put f of -3 in, I should get a 0. And what's more is whatever I get here is always the remainder upon division by the x minus whatever. If that's an h, then the x minus h. And we'll see that when we look at the long division, why that is. But essentially, when you, rather than long dividing, you can actually anticipate whether it'll be a factor right away. If you plug it in and you get 0, then you know it's a factor. Otherwise, you know it's not going to be a factor. Before we go there, we need to look at long division. Let's just remind ourselves what long division looked like back in the day. Some of you may have just done this, but bear with me here. Let's say you were taking 345 and dividing it by 12. A lot of people forget how to do this, even though this is like way back. So let me just write out that statement. What we're doing is 345 divided by 12. Now this is going to be too big. I actually have to alter my example because I don't want to make it too complicated here. Okay. So then I would, once I guess, and with polynomials, we're only going to be looking at the front number. There's no way to like do any more. We're just looking at that first number to see if what happens now when I multiply this 3 by the 12, I'm going to get 36. So remember, we guessed, we then multiplied, and then we would subtract to see what's left. And in this case, I have 1 left, and then 18, where I drop that to continue. And then now I'm trying to put this 12 into this new 18, and that's going to go right above the end of that. It's very important to align everything. So just a quick review here, you would say, okay, it goes in once, and I multiply it back to check it, and then I subtract it, and I say, well, there's 6 left over. So what that tells me is that 378 divided by 12 is 31 and 6/12, because the 6 is the remainder that has not yet been divided by the divisor. This is the quotient, right? Another way to write this is that 378 is equal to 31 times 12 plus the remainder. And this is going to be one of our more useful forms because we're taking that initial polynomial and we're trying to separate it into the factors and the remainder. So the quotient times the divisor plus the remainder. Okay, so now let's apply that to, that same strategy is going to be applied to polynomials. So let's say I was doing x plus 2 going into 3x squared plus 7x plus 8. And the reason why this can be pretty much exactly the same is if x was 10, this would be a 12, and then that would be 378. So it's exactly the same process because it's kind of like place value. Polynomials are like place value. Okay, so let's run through this. You would go, the x plus 2 is going into the first 2 terms. And I can only look at the leading term in order to decide. So I know that the x must be multiplied by, and I would put it, you always want to make sure that if you are multiplying by an x term, it is lined up above the x terms, not above the x squared terms. You want x squares to be all in a row, x's in a row, like your place values are all in the same rows. So I want to multiply by 3x because when I multiply this back, then that leading term, 3 times 2, 6, is going to cancel. And I want that leading term to cancel. I can't have anything there. The trick here that you have to be really careful of is now when you're subtracting, this minus applies to both terms, right? So I'm going 3x squared minus 3x squared, which is 0, x squares. And then 7x minus positive 6x. You might want to change that sign or somehow indicate to yourself that you are minusing. So 7 minus positive 6 is positive 1x. Okay, so that's one step. But now we still have to deal with that 8. I'm going to drop that 8. And now I'm going to think about what's going to go here. And so now in my second step, I'm looking at this as this going into that. And so I think, how many times will I have to multiply? And really, I just want a 1 here because 1 times x is going to be 1x. 1 times 2 is going to be plus 2. And you're doing that same subtraction step now. This will be 0. 8 minus 2 is 6. That's pretty much exactly what we got, 31, remainder 6. So 2 ways to write this. One way is to say that 3x squared plus 7x plus 8 can be written as 3x plus 1 times x plus 2 plus 6. So that's this format where you have the quotient times the divisor plus the remainder. Or another way to write it, depending on what format they want as an output, is that 3x squared plus 7x plus 8 divided by x plus 2 is the quotient plus the remainder that has not yet been divided by. Right, these are two kind of formats of a solution. They are useful in different cases. This first one really helps you see that that remainder is left when you put in the opposite of what you're dividing by. So if you're dividing by an x plus 2, right, you're dividing by x plus 2. So if this is my f of x, then if I put a negative 2 in, what am I going to get? Well, if I put a negative 2 in, it's going to zero this thing out. And I'm just going to get a 6 left, which means this is my remainder upon f of x divided by x plus 2. Right? You can see that because that would zero out right here. That's useful to us because in the future, rather than doing all this for every number, we can just plug in a negative 2 and see if it gives us 0 or not. And we can wait until we get a factor that will actually factor completely and not just with a remainder. Because we want to be able to get that remainder to be 0 so that it factors completely so we can find all the other zeros. So essentially what you're leading to is you're going to be given some f of x and you're going to be asked to factor or find zeros, which is really the same thing. When it's a higher degree polynomial, we're going to have to first break it down and see, okay, can we find 1, 0? Once we can find 1, 0, we can use the long division process to then find the other zeros. So this is where we use it. So this one's a cubic, right? And the reason why I'm saying what happens at x equals 2 is because perhaps that is a suggestion of what the 0 might be. The first types of questions that you'll have, they will give you a k that could work, and they just want you to write it in the format. Maybe it has a remainder, maybe it doesn't have a remainder. But eventually what we're trying to do is we're trying to get the remainder to be 0 so that we can factor. Now, I do want to mention that there is a slightly quicker and simpler way to long divide. So let's try that on, which example did I want to do that on? Yeah, I wanted to do that one on the 4. Yeah, okay. So first of all, let's identify like what happens at x equals 2. So if we want to figure out what happens at x equals 2, we can just go f of 2 is 4 times 2 cubed minus 5 times 2 squared plus 2 times 2 minus 10. Okay, so all this means is at 2, it's going to be a 1. I've identified that by the graph, but you could calculate it. All this means is that x minus 2 will not be an equal factor. Like it won't be a 0 factor. But I can still run this process and figure out what the remainder is upon division by x minus 2. And so we'll still do that division. It's just that it's not like when you see the graph actually only has, see how this cubic, it's just like, it actually only has 1, 0. So it's got a little bit of, it's not like one of those perfect looking ones with the 3 perfect zeros. But that's okay, we can still process the division on it. So one way to divide is going to be to go the x minus 2 going into 4x cubed minus 5x squared plus 2x minus 10. The important thing here is that you have all the place values. So if you have x cubed, x squared, x to the 1, and x to the 0. We often don't write the x to the 0, but if it's a constant term, it has an x to the 0. If you're missing any one of these, like if you're missing the 2x, you still would need to make it a 0x to fill that spot. If you don't fill that spot, your whole process is going to be wrong. So be really careful to make sure these are all there. Okay. So yeah, so why don't you see if you can try this process out, right? You're trying to put this into that. So we'll do it this way, and then I'm going to show you kind of like the synthetic division, which is kind of like a reduction of this whole process, but both ways are useful. I mean, eventually you might just like doing synthetic division because it's quicker, but it's less transparent in terms of how it works. So let's try this out. X minus 2, you're trying to make sure that that first term aligns. So you're going to multiply by 4x squared. Because when you go 4x squared times these two, you're going to have 4x cubed minus 8x squared. Okay, and then minus all of this. So the first term is going to disappear. So that's good, but then now you have to be careful as you read this. Negative 5x squared minus negative 8x squared is negative 5, and then plus 8 is going to be 3x squared. So that's what's left from that first multiplication. I'll do a different color for the next layer. I'm going to drop this down, and now I'm looking at this, and I'm trying to get that to multiply into that. So I need a 3. So plus 3x, and notice how these are aligned. They're the same power. Everything's aligned. Use graph paper, create space. Some people who write it too squished always make mistakes because it's just too tight. So make space for yourself. 3x times x, 3x squared. 3x times -2, negative 6x, yeah? And minus all of that. Now let's just double check that that's all good there. Yeah, so the 3x squares disappear, so that's good, that's gone. And then the 2x minus the -6x is going to be 2 plus 6, which is 8x. And then now I'm going to drop the last one, say in black. And so now I can go minus or plus 8. 8 times x minus 2 is, we have that, I believe. Let's try it. So 8 times x minus 2, 8x minus 16, yeah. So then the minus 10 plus 16 is going to be our 6. You could write it in a couple different ways. You could say that f of x is x minus 2 times the quotient and then plus the remainder. Okay, that's our standard way. Our goal later on is to find things that will produce a 0, because when the remainder is 0, we have a factored form, and then we can continue factoring this, and it makes it nicer. So let's do the other method of this is called synthetic division. So what we're going to do is we're going to take the leading coefficients of our polynomial, and you again have to make sure you have all the components. So the cube, the square, the power of 1, the power of 0. If one of those is missing, it's a 0. So I'm going to write that out, but I'm only going to write the leading coefficients of it. So 4, -5, 2, and -10. So again, this is a very reductionist sort of approach, but it kind of yields the same effect as that left-hand side process. Okay, so we're taking this, and the synthetic division, whereas this is long division, is going to only work if we are dividing by x minus whatever number, letter, or like I'm going to write k here. Because we're dividing here by x minus 2, then I'm going to be interested in that k is going to be the number that I'm, the opposite of the number that I'm doing. So if I was dividing by x plus 5, the number here would be -5. If I'm dividing by x minus 2, the number here is going to be a positive 2. So it's opposite to this number, but it's the same as this number. That always gets a little confusing, but once you get it, then you can proceed with it. So what they do is, here's the process. You take the first number, you drop it down, but then now you multiply these, 2 times 4, and you write it here. 2 times 4 is 8. Okay, now you're going -5 plus 8. Notice that that is very similar to what you were doing here, and you get 3. And now you're going to do the same thing again. So I'll try and draw it in a different color. Going 2 times 3, putting it there, 6. And you're going 2 plus 6. Notice you get the same thing that you did here. So it's kind of a reduction of the entire process that we were doing with the long division. And again, the limitation is it only works for linear factors like that. It does not work for division by any other higher degree polynomials. And that's why they teach both in the course. Okay, and then the next, you can anticipate 2 times 8. It's going to be 16. And so when you add that, 16 minus 10 is 6. So again, you're adding here. Okay, now look at how this relates to the left-hand side. Those are the coefficients of your quotient, and this is your remainder. So what this tells you is that f of x upon division by x minus 2 results in 4, and then you're going to have to include these variables, and then plus the 6. Okay, so it's a little bit easier to do the synthetic division, I agree, but again, it only works for linear factors, which is mostly what you're doing in this course, but you want to be aware of both of those strategies in case you were dividing by something like 2x minus 3. If you were dividing by that, synthetic division wouldn't really work. Or if you were dividing by something with a square, also synthetic wouldn't work. So synthetic's really useful, but only for a limited type of example. Okay, so how does this help us? What this helps us is to see that, okay, x minus 2 is not a factor, 2 is not a 0. Upon division by 2, like if I plugged in x equals 2, I should get a 6. This should actually be a 6. Oh yeah, so look, at 2, it is at 6. Where it will help us is if we divided by something that was a 0, that gave us 0 right away, then the division would produce just that plus 0, and then you could factor this, and then you'd have all of the factors. Okay, so that's what we're going to be getting to. Next class, we're going to be looking at how do we identify the number that for sure is going to give us a 0, and then how do we take that so that we can factor it and find all the zeros and not be stuck with a remainder. I'm just trying to find one where it is actually going to factor nicely. Oh, okay, here we go. Here's a nice example. I got one. Okay, so obviously we can graph this, and it's kind of cheating, but we can see that this should have and will have 3 zeros. The problem is historically, they didn't have calculators like this on iPads. And so this whole study was done with no technology, and the whole process of what Mod 4 is teaching you is the historical approach of how they would have identified the exact values of these zeros without any graphing tools. So one thing is any of these 3 zeros should go in, and if you plug in a 2, for instance, into x, you're going to get 0. So let's say once you have that, and once you know that, say, x minus 2 is a factor, so you've checked f of 2, you do it and you get 0, and you're like, yay, I know that's a factor. Then you can either divide by the x minus 2 with long division, which I won't do here, or you could use the 2 in a synthetic division. In this case, that would be 1, 3, negative 6, 8. So if we do that, drop the first number, multiply by 2, add. Multiply by 2, add. Multiply by 2, add. Look at that. We get a remainder of 0, and this is the rest of it. What that tells me is that f of x is going to be x minus 2 times x squared, 1x squared, plus 5x plus 4 plus 0, right? That's important because now I can take this, I can factor that with my regular factoring techniques, and then I can have all the other zeros. So once I have 1 0, I see the rest of the zeros. So that's the kind of, yeah. So what's that going to be? Product 1 and 4, x plus 1, x plus 4, I think is going to work. And therefore you have zeros at 2, negative 1, negative 4, which is what we have. Okay, so you can imagine that having these strategies and having no graphing calculator is what would help you get those factors.